Hello everyone, we've been talking about confidence intervals for a few days, and today we're going to get into the mechanics of estimating a population proportion by constructing a confidence interval for a proportion. In this scenario, we want to estimate the proportion P of pennies more than 10 years old in a particular collection. And if the collection is really large, you probably don't want to actually go through and count all the pennies and separate them into piles of more than 10 years old and at most 10 years old. So Mrs. Smith's class sampled 57 pennies, and were actually 102 pennies. 57 of them were more than 10 years old, and 45 were 10 years old or younger. And to construct our confidence interval, we need to first make sure the conditions for constructing a confidence interval for a population proportion P are met. And these are conditions we've taken a look at already. One, as you can have already guessed, is simple random sample. We're going to assume that the pennies are well mixed and that the sample was selected at random. The second condition is that there's at least 10 successes and 10 failures. This allows us to use normal distribution approximations. And let's see, at least 10 pennies that were more than 10 years old and at least 10 that were, this should really say 10 years old or younger. Let's see, we had 57 and 45, so that condition's met. And the last condition is the 10% condition. We want to make sure, since we're sampling without replacement, that we sample no more than 10% of the population, and we had 102 pennies in total. It's safe to assume that the collection has more than 1,020 pennies. So now we're ready to actually construct the confidence interval. And if you remember, a confidence interval is constructed by taking a look at a sample statistic, and then we add and subtract our critical value, which we call Z star, and we multiply that by the standard deviation of the statistic. This critical value depends on the level of confidence. The best way to get the particular Z star value is to actually use a new table in your textbook. Let me show you where that's at. So if you go to your book and you go to tables and we go to the next table here, this table B, our t distribution. If we scroll down here, and let me make this a little bit bigger so we can see it. If we scroll down here towards the bottom, we can see that there are Z star values here for different levels of confidence. Notice 96% confidence, 98% confidence, 95% confidence is what we often use, this 1.96 value here at the bottom of the table. So our Z star values we can find easily just by using this table. So let's use 1.96 since we're talking about a 95% confidence interval. So our Z star value would be 1.96. Our sample size N was 102. That was the 57 plus 45. And our p hat value is the proportion of pennies that are more than 10 years old in the sample, and that would be 57 out of 102. So her claim is that in her collection, 62% of the pennies are more than 10 years old. And obviously we're not going to get exactly 62% in a single sample, but the question should be, is our sample so far off that we think 62% is not a plausible value? And we're going to construct a confidence interval to help us figure this out. So here's our confidence interval calculation. We have our sample proportion, 57 divided by 102, that's about 0.559. So that goes in place of p hat. Our critical value for a 95% confidence interval is 1.96, and our sample size, n, is 102. So we'll do the calculation here. And my confidence interval is 0.559 plus or minus 0.096. If we add and subtract the margin of error, that's what this is referred to as, the margin of error, to our sample proportion, we'll actually get this lower bound and this upper bound for our interval. So if we want to interpret this, we would say we are 95% confident that the interval 0.463 to 0.655 contains the true proportion of pennies in the collection that are more than 10 years old. Remember, Mrs. Smith claimed that 62% of her pennies were more than 10 years old. And since 62% is in this interval, 62% is a plausible value. Let's take a look at how our calculator could be used to help construct the confidence interval. So we hit Stat, and we go over to Test. Now this is a new area in our calculator that we haven't worked with before. Notice we have some things called tests, which we're going to get into eventually, called hypothesis testing. But we want to do a confidence interval. And we're working with a proportion, so we're going to choose one prop z int. And we're going to enter our number of successes, that's our x, which was 57, and our sample size n, which was 102. And it already has a 95% confidence level, so I don't have to enter anything there. And I hit calculate, and notice we get our sample proportion as well as the lower bound and the upper bound for our confidence interval. Let's take a look at a few more questions. So what's going to happen to our confidence interval if our confidence level is increased? Well, if our confidence level is increased, our z star value would be increasing. And what's that going to do to our interval? It's going to make it wider. What happens to a confidence interval if the sample size is increased? Well, let's think about that. If the sample size is increased, that means our denominator is going to get bigger here, and that means our standard error of our estimate is going to get smaller. So if our sample size is increased, that means that our interval is going to get narrower. Let's take a look at one final question. If our original sample size was 100 and we wanted to cut our margin of error in half, how would this be accomplished while keeping the same level of confidence? In other words, our numerator is going to be exactly the same because we haven't changed our value of p hat. Our z star value is going to be exactly the same because we're keeping the same level of confidence, but I want my margin of error to be half of what it was before. So this is inconsequential right now, and so is this. Well, the way this would work in terms of our sample size is, if you think about it, I could put this 2 back under the square root sign in my denominator, and if I did that, it would become a 4. So in other words, if I want to cut my margin of error in half, I need to have my sample size be 4 times the original sample size. We'll be continuing to work on this in class over the next few days.